Hello, everybody. This is Homer White with the first in a projected series of three screencasts on Section 5.3, Hypothesis Testing for a Proportion. So as usual, we may use some resources from the TigerStats package, so make sure that you have attached it to your R Sessions search path if you are following along with the code in these slides. So what are hypothesis tests? Well, we've been talking about population parameters and how we can use data to estimate them. There are actually three types of questions that you might ask about an unknown population parameter. Not two, actually three. First of all, given the data, what's my single best guess at the value of that unknown parameter? That is something that we addressed early on in the chapter. Your best guess at the value of the parameter is your point estimate of the parameter that you get from data. So for example, if you want to know the value of a population proportion P, you might use the sample proportion from your data. The next question is, what's the range of reasonable values for what that parameter might be, given the data that you have? And that second question we've learned can be answered with a confidence interval, usually a 95% confidence interval. And that gives the range of reasonable values for what P might be. But there's a third question that we want to address in this section. Given the data, is it reasonable to believe that the value of that population parameter is such and such, some particular amount that you might be curious about? And that third question is answered by performing what we call a test of hypothesis. So let's start off with just a sample survey question. If we were together in class, we might actually collect answers on it. Take a few seconds to think about this one. How many of the world's one-year-old children today have been vaccinated against some disease of any sort? Do you think it's closest to 20%, 50%, or 80%? So think about that for, say, 10 seconds. Okay, the correct answer turns out to be 80%. So we might be curious, let's let P be the proportion of all people with a four-year college degree who would get the correct answer. You know, maybe it's 0.10, maybe it's 0.25, maybe it's 0.378. We don't know what it is because we can't ask everybody in this population that question. So we don't know P. Now, let's just imagine two competing ideas about what P is. The first idea believes that P is a particular number, 1/3. This idea is called the Null hypothesis, written H with a little subscript underneath it. And it corresponds to the idea that there's no real difference between these options, these three options that we were given, and that people never learn about world vaccination rates. And so their responses are just equivalent to guessing randomly, in which case a third of them would guess the correct answer. Now, another idea simply disagrees with the Null hypothesis and says, P's not 1/3, might be more than a third, might be less than a third. This idea that disagrees with the null hypothesis is called the alternative hypothesis and is written H with a subscript A for alternative. So if you're a believer in the alternative hypothesis, you might go either way. You might believe that people have some knowledge about vaccination rates that helps them to do better than random guessing. That's p bigger than a third. Or maybe that they have something like anti-knowledge that leads them to do actually worse than random guessing, p less than a third. Either way, you're one of the people who supports the alternative hypothesis. So let's say we were able to survey 50 people who had four-year college degrees and got their responses. And say that we found that 12 of them, 12 out of the 50, that's the same as 24 out of 100, so it's 24%, got it right. And what we're wondering is this 24%, it's less than 1/3, which is 33%. Does this data provide strong evidence against the null hypothesis? So to answer this question of whether or not it's reasonable to believe that P is this specific value 1/3, that's what we perform a test of hypothesis to find out. Now you'll find that every test of hypothesis involves a test statistic. And for us, the test statistic was 0.24. The sample proportion was 0.24. And we're going to use this test statistic to decide if the null hypothesis's view that p equals 1/3 is really a reasonable view. So let's just assume for now, temporarily, just for the sake of argument, that null hypothesis is true. Okay? What then might that p hat tell us? How unusual would it be to get a sample proportion of 0.24 if the null is true? That's really our question at this point. Well, you'll remember that you can measure how unusual a value is by computing its z-score. So we'll do something like that here with p hat. We'll compute a number that we call z, and it's the p hat that we got minus what the null hypothesis thinks that p is, the 1/3. And we'll simply divide by the standard error of p hat. And so this z number is computing how many standard errors the p hat is going to be above or below what the null hypothesis expected it would come out to be around. Now, we do have this temporary assumption that p is really 1/3. So we can compute the standard error using our formula for standard error for p hat, just plugging in the null value of 1/3. So in R, let's go ahead and set up a little variable p0. That stands for the null value, so it's 1/3. And then we apply our formula for the standard error, which is the square root of the parameter times 1 minus the parameter divided by the sample size of 50. So we're calling that SE. The SE turns out to be 0.067 roughly, about 6.7%. Now we can get the test statistic. Remember, it's gotten by taking our sample proportion, subtract off the null value, divide by the standard error we just found. And so if you were entering into a calculator, you'd be doing 0.24 minus 0.333 over 0.06667. And you get around minus 1.4. Now, since you're working in R and using R like a calculator, you just have to do 0.24 minus P naught divided by the SE, and you get your minus 1.4. So that means that our sample proportion was about 1.4 standard errors below the null's belief about what P is. And remember, for us, our standard of what's unusual is that the z-score be more than 2 or less than minus 2. So our results are not so unusual. But let's be more precise. Exactly how unusual are these results? One way of measuring that is to find the probability of being 1.4 or more standard errors away, like what we got, if the null is really correct. That probability is called the p-value of the test. P is short here for probability. So how are we going to find that probability? Well, it would help to know something about the probability distribution of the sample proportion p hat. And remember that the sample proportion is going to be approximately normal if the expected number of successes and failures is at least 10. Well, the expected number of successes is the sample size times p. Sample size is 50. We're assuming temporarily that p is a third. That's 16.67 roughly, which is more than 10. The expected number of failures is n times 1 minus p, and again, that's more than 10. So the success-failure condition in the book tells us that p hat has approximately the normal distribution. So then we think about z. Z is gotten from p hat, which is normal. We're taking this normal random variable and subtracting off the expected value that it would have if the null is right, and dividing by its standard error. And so as we've learned, the z-score of a normal random variable turns into a normal random variable with mean 0 and standard deviation 1, the standard normal distribution. That means that we can find our p-value using the standard normal distribution. All we've got to do is head to p-norm GC. Remember, we're looking for the chance of being more than 1.4 standard errors away. So we're looking at the chance for z to be less than minus 1.4 or more than 1.4. So when we call p-norm GC, we set up two boundary numbers at minus 1.4 and 1.4, and we say that we want the area under the standard normal curve outside of that. We specify the standard normal curve by saying that the mean is 0 and the standard deviation is 1, and it's nice to ask for a graph. So we find that the p-value is about 0.16 down here at the bottom. That's the shaded area, the total shaded area that you see. These two pieces put together make about 16% of the total area underneath the standard normal curve. So that's the p-value, about 0.1615. What does it mean for us? Here's what it means. This is our interpretation of the p-value. If the null is right, if the population proportion really is 1/3, then there's about a 16% chance of getting results at least as extreme, at least as far away from what the null was expecting, as the ones that we got in this sample. That helps us to make a decision about the reasonableness of the null hypothesis in the face of this data that we have. Something that had about a 16% chance of happening, that's not so unlikely that it would happen. 16% is about 1 out of 6, you know. So about 1 out of 6 times that you do stuff, the thing would happen. So my decision is I'm not going to reject the null hypothesis. I'm not just going to write it off as unreasonable. This sample of 50 people may have provided some evidence that people are either better or worse than random guessers, but it didn't really provide strong convincing evidence to me that P was not 1/3. So we're not rejecting the null hypothesis, but let me be very careful to say that we're not, therefore, accepting the null hypothesis. Because after all, think about an actual population with millions of people and a proportion for that population. I mean, what's the chance that it would be exactly equal to a simple number like 1/3? Basically about zilch. So even though in my heart, I know that the real P probably is not exactly 1/3, I'm not, in my heart, I know the real P is probably not exactly 1/3, and that's why I'm not accepting the null hypothesis. My failure to reject the null hypothesis is just saying that the data that we have doesn't by itself rule out the null hypothesis as unreasonable. It's one of the reasonable values that one might believe in as far as what P might be. Let's vary this example a little bit. What if it had been a different survey where there were 200 people sampled? And what if 24% of them had gotten the correct answer? Let's redo the test using this data. So we still have the same old p hat of 0.24, but we're going to have to change our computation of the standard error because we have a new sample size of 200. The p naught is still the 1/3 that it was before, but the 200 here makes the standard error different. It's about 3.3% smaller than before. So when we head to find our test statistic, we have a little bit different standard error here at the bottom. That smaller standard error in the denominator means that the fraction is going to turn out to be larger in size, and it came out to be negative 2.8. You'll see that when you compute it in R. So that's a lot bigger in size than it was before. The results that we have in this sample are 2.8 standard errors below what the null was expecting them to be. The null thinks that P is 1/3, so it thinks that when you take a sample, you should get somewhere around 1/3 for your sample proportion. We got 2.8 standard errors below what the null thought we ought to be getting. That's a lot. What's the p-value? Well, you compute it the same way as before, except now you're looking for the area outside of the minus 2.8 to 2.8 range. And as you can see, that's a much smaller probability, 0.005, about 1/2 of 1%. So how do we interpret the p-value? It's this complete sentence here. If the null is right, if p really is 1/3, then there's only about a 0.5% chance of getting results at least as extreme as the ones we got in the sample. So now we arrive at a different decision than what we had with that smaller sample. Now we think if the null is right, then the results that we actually got would have been very unlikely to happen. So rather than believe that something very unlikely to happen just somehow happened, instead, we reject the null hypothesis. Looks like this sample of 200 people provided strong evidence that people are worse than random guessers we got a p-hat of 0.24, that's less than a third, it leads us to believe that the sample proportion is actually less than a third. So this is your decision, and this complete sentence here is your conclusion to your test of hypothesis. So the general idea for making a decision in a test of hypothesis is to look at the p-value that you computed. And the lower the p-value is, the worse it looks for the null hypothesis, the more inclined you should be to reject the null hypothesis. Just keep in mind, rejecting the null hypothesis does not mean that you're somehow 100% sure that the real value of p differs from the null value in whatever direction your data led you. Because your data is the result of a chance process when you sampled. So it's always possible that you got some really unusual sample. Also, remember that failing to reject the null hypothesis does not mean that you have to believe that the null hypothesis is true. It's just that your data didn't have enough evidence to say in which way the population parameter really differs from the null value. You might not believe, based on common sense, that the real parameter is exactly what the null says it is, but when you fail to reject the null, you're just admitting that that particular value is one of the reasonable values that p could be. Now, people always ask at this point, how small should the p-value be in order to reject the null hypothesis? And the real answer is that there is no one cutoff level. It all depends on context and the consequences of what your decision might be, the practical consequences of your decision. So the level of significance, the cutoff value that you choose, will depend on context. But a lot of people will use alpha to be 0.05. And we'll go ahead and use that value all the time unless we specifically say that we're going to do otherwise, for practice, or if there's a situation where it seems we ought to have a lower or a higher level of significance. So for you, the rule is going to be, if the p-value is less than 0.05, reject the null. If the p-value is bigger than 0.05, fail to reject the null. That's all for now. We'll continue in the next set of slides.